Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.3. Calculating Limits.
Lesson 1. The Limit Laws. The next section we'll be looking at is calculating limits using the limit laws. What we did in the last section was to understand what a limit is by calculating the limit from a graph, or sometimes we used a table. So that's what we've done so far, is to use graphs and tables. There is a problem with using graphs and tables, of course. First of all, if we are to calculate a limit of some function y equals f of x using a graph, first of all, we would have to graph the thing, which is a lot of trouble. Even if you use a graphing calculator or some other graphing device, it can also be very inaccurate. If we look at this just as an example, here's y equals f of x. Suppose I wanted the limit as x approaches 10, say from the right of this function, f of x. I wondered what that limit was equal to. Well, of course, I can use the graph to do that the way that we talked about before. You could put something like 11 into this graph and go up to the function over the y-axis, hit some output value. Perhaps we would hit 6. You could put in 10.5. Go up to the graph and over, and you might guess that the limiting value as we get closer and closer to 10 from the right is equal to the output value 5. So you might guess that the answer to this problem would be 5. But what if in fact this is getting closer and closer to something that's close to 5 but perhaps a little bit larger? What if the true limit is actually a little bit above 5 and the true limit is 5.1? It would be very difficult to tell from a crude graph like this that the limit of this function was in fact 5.1 rather than 5. So that's one of the limitations of getting a limit from the graph. The same thing is true with the table. Here I have x values for this same function where the x's are 11, 10.5, 10.1, 10.01, 10.001. So my x's are getting closer and closer to 10 from the right-hand side. And the output values are 6, 5.4, 5.2, 5.13, 5.11. And again, you might be tempted, because we like to think in round numbers, to guess that the limit is 5. But perhaps that's not correct, and the actual limit is 5.1. It would be very difficult to tell from a little scattering of evidence like this that the limit is in fact 5.1 rather than 5 just by using a table. So that's the limitation of using a graph or a table as we did in the last section. What we would like to do is know how to find the limit of a function directly from the equation of the function. So that's what we'll be talking about in this section. One thing that I want to remark is that we will be talking about a bunch of limit laws. They are essentially theorems about limits. And in order to prove all of the theorems or limit laws that we'll be discussing, you actually need the precise definition of limit, which we did not cover in the last section. So I'm not going to prove these laws. I will try to give you some kind of intuitive idea of why they would be true. I think most of them will make sense to you because we will use pictures or some kind of argument to back them up. But we will not be doing careful proofs of these theorems. All right. The way that we are going to approach finding the limit of a function from its equation is to try to take a difficult expression for a function and break it down into simpler parts that we can find the limits of. So we're going to start with two very simple building block limits, and rather amazingly, from these two building block limits, we'll be able to find limits of very, very complicated algebraic functions. So let's look at the first example that I have here. I'm going to find the limit as x approaches 3 of the function 5. You notice there are no x's in here at all. It's a constant function. In fact, I could graph that function y equals 5, where the output is always equal to the constant number 5. That's why we call it a constant function. If I were to graph this, remember that y equal to a constant is a horizontal line, all of whose output values, all of whose y values are constantly equal to 5. So you might remember that the graph of this function would look something like this. And we know how to find a limit from a graph. If I want to find the limit of this function as x approaches 3, I could look at the limit from the right, and I can see that if I plug in a value to the right of 3, say I plug in something like 3.2 or 3.1, I go up to my graph and go over, and since it's a horizontal line, I actually hit the y value at the number 5. If I choose something even closer to 3, say I choose 3.1, I'm going to go up to the graph and go straight over to the y-axis, and I hit the number 5 again. So if I ask what's the limit as I approach 3 from the right of this function, well, are the y values collecting around a single number? They are. In fact, they're all equal to the same number, namely the number 5. So the limit of this function would be equal to 5 as we approach 3 from the right. Same argument would work from the left. If I choose something like 2.8 for my input value, go up to the graph and over, I again hit the number 5 on the y-axis. If I choose 2.9, something even closer to 3, but a little bit to the left of 3, I again get the output number 5. Not only are all the y values collecting around a single number, they're actually all equal to the same number 5. So if I ask for the overall limit of this function as x approaches 3 from both directions, we would say that the limit of this function is just equal to 5. In fact, it's the same number as what our constant function is equal to. The limit as x approaches 3 of 5 is just equal to 5. And really, it doesn't even matter what value x is approaching. If I were to ask you to find the limit as x approaches, say, 1 of this same function 5, that would just mean that I would be approaching 1 from both directions. And just like in the case of approaching 3 from both directions, if I approach 1 from the right and the left, all of the output values are equal to 5, and so the limit from the right and the left would again be equal to 5. What if I asked you an example like this? Find the limit as x approaches -6 of the number root 2. Remember that square root of 2 is just a number. It's irrational, but it's approximately equal to 1.4. So this is again the limit of a constant function that just happens not to be an integer value. It's the number square root of 2. So if I asked you to find the limit of this function, it would have a graph that's similar to this one, except that I would have y equals square root of 2, which remember is about equal to 1.4. That's probably good enough for a rough graph. And if I graphed this function, here's 1 and 2 on the y-axis, it would be a horizontal line that's right at the height about 1.4. So that would be the graph of y equals square root of 2. And if I were to ask you to find the limit as x approaches the number -6 from both directions, the right and the left, I hope you can see that as we approach -6 from the right side, all of our output values would be equal to this number, square root of 2. And if I approach -6 from the left side, all of our output values would be equal to this number, square root of 2. And so the limit as x approaches -6 from both directions of the constant function, square root of 2, would just be that constant, would be the number square root of 2. Let's think about this question in general. Suppose I asked you to find the limit as x approaches any given number a, so we're going to be approaching a on the x-axis, of the constant function c. So we're looking at the function f of x, or y, is equal to c. Well, just like we had up here with the limit as x approaches the number 3, that's our a value, of 5, that's our c value, the limit of this constant function is going to just equal that constant. If I were to graph this, you can perhaps see it a little bit better. Y equals c is a horizontal line that's at the height c on the y-axis. And if I approach x equal a from either the right side or the left side, all of my output values are going to be equal to that number c. And so the y values are collecting around a single number. In fact, they're all equal to that single number. And the limit as x approaches a of c would just be equal to that number c. In words, we say that this building block limit is the following. The limit of a constant is, and let's try to fill in these two blanks, is blank blank, is equal to, I guess we really should have 3 blanks here, is equal to that constant. So when we want the limit as x approaches any number a of the constant function c, we're going to get the output value c there. This building block limit is usually referred to as the limit of a constant. And what we really mean by that is the limit of a constant function. And the limit of any constant is just equal to that constant. Okay, let's go ahead and see if we can use this to try one other example. I'll just squeeze one in down here. If I ask you to find the limit, say as x approaches 5, of the constant number 1000, what would that limit be equal to? It doesn't really matter what x is approaching. I could have put 5 here, I could have put 17, I could have put 20,000. But the limit of this constant function is just equal to that constant. So the limit as x approaches 5 of 1000 would just be equal to 1000. Let's go ahead and turn to the next page. And there we're going to look at our second building block limit. The first one was the limit of a constant. And now we're going to look at this example to help us get to our second building block limit, the limit as x approaches the number 3 of a very simple function, just the function x. So this is no longer a constant function. We do have an x involved. But if I were to graph this function, f of x equals x, or for graphing purposes, y is equal to x, remember that that is a straight line. It has a y-intercept of 0 and a slope of 1, or you could think of it as 1 over 1. So we go up 1 and over 1 to get to another point on the graph. It's a line that goes through the origin at 45 degrees. So it looks something like this. Let's go ahead and find the limit graphically, and then we can try to write down a law in general. If I were to approach 3 from the right side, I go up to my graph and over. It looks like I get an output value that's maybe just a little bit larger than 3. If I choose something like 3.1 that's a little bit closer to 3, I will get an output value that's, well, actually the output value would be 3.1 because my y value is equal to my x value in this case. So if I put 3.2 in for an input, I would get 3.2 as an output. If I put in 3.1 as an input, I would get 3.1 as an output. The closer my x gets to 3, the closer my y's get to 3. So the limit from the right-hand side would just be equal to 3. Same type of argument if I approach 3 from the left. If I plugged in something like 2.8 for my x value, I would get 2.8 for my y value, because remember, we're looking at the function y equals x. If I put in 2.9 for my x value, I would get 2.9 for my y value. The closer my x's get to 3, the closer my y's get to 3. And so the limit from the left as x approaches 3 is also equal to the number 3. The left-hand limit and the right-hand limit are the same, and so the overall limit, as I approach 3 from both directions, the y values are approaching the number 3 on the y-axis. They're getting closer and closer to 3, and so we say the limit is equal to 3. Well, this is sometimes known as the obvious limit. And why is it called the obvious limit? It's because we're asking, as x gets closer and closer to 3, what's happening to x? Because our function is actually the same as just the x that we're allowing to approach 3. So as x gets closer and closer to 3, of course, this very simple function y equals x is going to get closer and closer to 3. And that's why we call it the obvious limit. Let's write it down in general. The limit as x approaches some other number, a, of the very simple function x is going to be equal to the number a. As x gets closer and closer to a, the function, which happens to be just x, is also going to get closer and closer to a. So that's referred to as the obvious limit. So we have the limit of a constant, that's what we did on the previous page, and the limit of a constant is just that constant. And we have the limit of x as x approaches a, and that's the obvious limit, and that limit is just equal to a. Let's look at this example. The limit as x approaches 1,000 of x. Well, if x is approaching 1,000, then our function x must also be approaching 1,000. That's the obvious limit. How about the limit as x approaches pi of x? Remember that pi is also just a number. Again, it's an irrational number, but it's about equal to 3.14 roughly, so I'll say approximately. So as x gets closer and closer to pi, what happens to x? It must get closer and closer to that same value, pi. If I ask you to find the limit as x approaches negative 17 of x, what would that be equal to? Well, according to the obvious limit, if x is approaching negative 17, then the function x is approaching negative 17. Well, believe it or not, these two building block limits, along with the limit laws that we're about to learn, are enough to find the limit of all kinds of different algebraic functions. In fact, most algebraic functions. So let's start to look at some of our limit laws, and we'll use them in combination with these two building block limits that we just discussed. Okay, first limit law. Suppose that we know that the limit as x approaches a of f of x and the limit as x approaches a of some other function, g of x, both exist and equal some particular numbers. This is what's going to be referred to as our sum limit law. When we want to find the limit as x approaches a of the sum of our two functions, the sum function f of x plus g of x, it turns out that we can just find the sum of the individual limits. In other words, the limit as x approaches a of f of x plus g of x, that more complicated sum function, can be broken down into two simpler limits. The limit as x approaches a of f of x plus the limit as x approaches a of g of x. We take a more complicated sum function, and to find its limit, we break it into two smaller limits, which hopefully we can find. In words, we say the limit of a sum is, so the limit of a sum of two functions is the sum of the individual limits. So I'll write down here is the sum of the limits. And so the limit of a sum is the sum of the limits, and this is referred to as the sum limit law, or the sum limit theorem. Let's look at some examples, and I think it will help to make this sum law make more sense and understand why it would be helpful. So let's turn to the next page, and at the top we have an example. We are supposed to find the limit as x approaches 3 of the function x plus 5. So this is a more complicated function than we have looked at before. Of course, we could graph it and find the limit that way, but that takes time, and it can also be somewhat inaccurate, as we discussed at the beginning of this lesson. So instead, what we're going to do is take this sum and break it into two easier limits. So the limit of this sum function is the same as the sum of the individual limits. So this would be the same as the limit as x approaches 3 of x plus the limit as x approaches 3 of 5. And hopefully these simpler limits are ones that we know how to do. Well, do we know how to do these? Do we know how to find the limit as x approaches 3 of x? Remember that that is just the obvious limit. In fact, we did this exact example on the previous page. And so, yeah, we know how to find the limit as x approaches 3 of x. That's our obvious limit. And remember that as x gets closer and closer to 3, x will get closer and closer to 3. And so this first limit is just equal to the number 3. How about the second limit? Limit as x approaches 3 of 5. Well, 5 is a constant function, so that's the limit of a constant. And remember, the limit of a constant is just that constant. So the limit as x approaches 3 of 5 is the limit of a constant function 5, and that limit should just be equal to our constant. That will be equal to the number 5. So the limit as x approaches 3 of x plus 5 can be found by breaking it into two smaller limits. These turn out to be limits that we already knew how to do from our building block limits. And so the answer to our original problem would be 8, 3 plus 5. So the limit of this sum function is equal to the sum of the individual limits. We were able to find those, and so our answer would be 8. Okay, we have a similar limit law for the difference of two functions. If I want the limit as x approaches a of f of x minus g of x, again, I can just take the difference of the individual limits. It would be the limit as x approaches a of f of x minus the limit as x approaches a of g of x. In words, we say the limit of the difference is, do you want to try to fill in the blank? It's the same as the difference of the individual limits, or we sometimes shorthand that to just say is the difference of, I should have put the in there, is the difference of the limits. The limit of the difference of two functions is the same as the difference of the individual limits. So the difference of the limits. And that's usually referred to as the difference limit law. We have another basic limit law here. The limit as x approaches a of c, where c again is a constant, times f of x. So the limit as x approaches a of a constant times a function turns out to be exactly the same as taking whatever that constant is and multiplying it by the limit as x approaches a of just f of x. This is referred to as the constant multiple law, as opposed to that building block limit that we talked about earlier, which is the limit of a constant. But this is the limit of a constant multiple. We have c times some other function f of x, and that's the same as a constant times the limit as x approaches a of f of x. So if we know how to find this limit of just f of x, then we can simply multiply it by the number c. Sometimes what we say in words is that we can take this constant multiple and pull it outside of the limit sign. So we can pull that c out front, and it's the same as c times the limit as x approaches a of f of x. And in words, we say the limit of a constant times a function, let's see if we can fill that in, is the same as the constant times the limit of the function. So the limit of a constant times a function is the same as the constant times the limit of just that function f of x. Let's try it with an example. I think it will make more sense. Suppose I want to do the limit as x approaches 3 of 7 times x. Put a little dot in there if you want to. Well, what this constant multiple law says is that we are allowed to take this 7 and pull it outside of the limit sign, and this is going to be equal to that constant 7 times the limit as x approaches 3 of x. Is this a limit that we know how to do? It's the obvious limit again. It's one of our building block limits. And so this would be the same as 7 times. And we know the limit as x approaches 3 of x is just going to be equal to the number 3. That was our obvious limit. And so the answer to our original problem would be 7 times 3, or 21. So you can see how we can take the limit of a more complicated function and break it down into things that are simpler limits to do, that hopefully we know how to do because they're one of our 2 building block limits. Okay, a fourth limit law, limit as x approaches a of f of x times g of x. Just as you might guess, the limit of this product of 2 functions, multiplying 2 functions together, we can do by finding the individual limits, taking those numbers and multiplying them together. So the limit as x approaches a of f of x times g of x is exactly the same as if we did the limit as x approaches a of f of x and multiplied that by the limit as x approaches a of g of x. If you want to, you can put parentheses around these to make it clear that we're doing the limit of f of x and the limit of g of x separately. We're finding those answers and then we're multiplying those answers together. In words, we say the limit of the product meaning to multiply, is, and maybe you want to think about how to fill in the rest, the limit of a product is the same as the product of the original limits. So we say is the product of the limits. And this is usually referred to as the product rule or the product law of limits. Okay, let's try this one on another example. And I think, again, doing examples helps us to understand these things a little bit better. Suppose I had the limit as x approaches 3 of 7x, that function, times x, very simple function. According to the product law, I can just go ahead and say, well, that is the same as the limit as x approaches 3 of my first function, 7x, times the limit as x approaches 3 of my second function, which is just the function x. Of course, now the question becomes, can we do each of these limits? If I look at the first limit, it's actually the example we did on the previous page, and it involves the limit of a constant multiple, 7 times x. If we hadn't done that already on the previous page, we would just say, oh, okay, 7 is a constant multiple, and a constant multiple we are allowed to pull to the outside of the limit sign, so that this would be the same as 7 times the limit as x approaches 3 of x, and then I'm going to pull down this other limit that we had, times the limit as x approaches 3 of x. Each of the limits that we have left is just the obvious limit. It's one of our building block limits. So I carry the 7 multiplied by along, and the limit as x approaches 3 of x, that's the obvious limit, so that's just the number 3. This is exactly the same limit, so its answer would also be 3. And the answer to my original problem would just be 7 times 3 times 3. So that would be 21 times 3. That would be 63. And so the answer to my original problem would be the number 63. Okay, let's try this limit law. This says the limit as x approaches a of f of x divided by g of x is equal to, and you can probably guess that to find the limit of a quotient of 2 functions like this, we can find the limit of the top, get a number, and just divide by the limit of the bottom, whatever number that turns out to be. So the limit as x approaches a of f of x over g of x is just the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Now you notice there's a little space over here. It says provided, and you might think about this a little bit. When we find the limit of the top, we'll get some number. When we find the limit of the bottom, we'll get some number. And the limit of this quotient will be equal to the quotient of these individual numbers, these individual limits, provided. And can you think of what problem might possibly come up when we're doing a division that didn't come up when we were doing a multiplication. Yeah, this limit that's on the bottom, you wouldn't want that to come out to be 0 because we can't divide by 0. We would get something that's undefined as an answer. So there is a little proviso over here that we have to put in, provided that the limit in the denominator, the limit as x approaches a of g of x, is not equal to 0. If it is equal to 0, then this original limit may or may not exist, but we cannot find it by using this particular limit law. But as long as the limit in the bottom is not 0, we can simply find the limit in the top, find the limit in the bottom, and divide those two numbers. So the limit of the quotient is the quotient of the limits, with this provision that we have over here. So it really, if we were to complete this sentence formally, we'd have to say provided the limit in the denominator is not 0, provided the limit as x approaches a of g of x doesn't turn out to be equal to 0. Well, let's see if we can go ahead and apply that to an example, make it make a little bit more sense. We're going to find the limit as x approaches 3 of x divided by x plus 5. Well, how do we do that? According to this quotient law of limits, I can go ahead and break this up into the limit as x approaches 3 of the top, x, that's my function in the top, divided by the limit as x approaches 3 of the bottom, which is the function x plus 5. So I can find the limit in the top and the limit in the bottom separately and just divide those two numbers by each other, provided the limit in the bottom is not 0. If the limit in the bottom is 0, we'll talk about what happens with that at a later point, so don't worry too much about that at this moment. Well, can we find the limit in the top? Sure, it's just the obvious limit. The limit as x approaches 3 of x is just the number 3. So the limit in the top we can find, and it is equal to the number 3. What about the limit in the denominator? Well, that's a sum. It's actually one of the examples that we did on the previous page. If we hadn't done that one, you could still say, well, it's the limit of a sum, and so I can do the limit as x approaches 3 of the first function, x, plus the limit as x approaches 3 of the second function, 5. And each of those limits we can figure out pretty easily. Limit as x approaches 3 of x, that's the obvious limit, so that would just be the number 3. And the limit as x approaches 3 of 5, that's the limit of a constant, and the limit of a constant is that constant, so that would be 5. And so overall, the limit of my original problem would be 3 divided by 8. And you notice that the limit of the function in the bottom of x plus 5 was not equal to 0, and that says that we are allowed to use this particular limit law to find the limit. We just find the limit in the top, find the limit in the bottom, and we divide those two numbers, and we would get a final answer of the number 3/8. Just as a side remark, all of the limit laws that we've just talked about also hold for one-sided limits. So, for example, if instead of finding the limit as x approaches 3 of x over x plus 5, if I asked you to find the limit as x approaches 3 from the left of x over x plus 5, we would still be allowed to apply exactly the same limit laws, and we could apply the quotient limit law and say, well, this would be the same as the limit as x approaches 3 from the left of the function that's in the top, which is just x, divided by the limit as x approaches 3 from the left of the function in the bottom, which is x plus 5. And the obvious limit holds for a left-handed limit as well as an overall limit. So the limit as x approaches 3 from the left of x is just equal to the number 3. That's the obvious limit. And in the denominator, again, you could break it up into the limit as x approaches 3 from the left of x plus the limit as x approaches 3 from the left of 5, using the sum law for a one-sided limit, a left-hand limit. And you would end up with exactly the same numbers in the bottom. Limit as x approaches 3 from the left of x is 3, and the limit as x approaches 3 from the left of 5, the constant 5, is just equal to 5. So these same limit laws hold. Both the building block limits, the limit of a constant and the obvious limit, and all of the other limit laws that we talked about, the sum law, the difference law, the product law, and the quotient law, hold even if we're not doing an overall limit, but if we're doing a limit from the left or a limit from the right. So let's go ahead and look at this example. It will ask us to use our limit laws. We're going to use the limit laws to find the limit as x approaches 4 of f of x minus g of x. But in this case, instead of being given an expression for f of x and for g of x, we're given the graphs. And you can see over here on the right, this is the graph of f of x. It's graphed in black. And here's the graph of y equal g of x. That is graphed in blue. If I want to find the limit as x approaches 4 of f of x minus g of x, remember that we are allowed to go ahead and break this up. We can use the difference limit law, and the limit of the difference is the same as the difference of the individual limits. So this would be equal to the limit as x approaches 4 of just f of x minus the limit as x approaches 4 of g of x. Well, the question becomes, can we find these individual limits? Let's concentrate first on just the limit as x approaches 4 of f of x. Well, I just do that the way we did in the previous section. I can get that limit from the graph. So if I want to do this particular limit, concentrating on limit as x approaches 4 of f of x, I can do it by first finding the left and right hand limits, seeing if they exist and are the same. If I approach 4 from the right hand side, it looks like the outputs are collecting around, it's a little hard to see on here, but it looks like they're collecting around the number 2 on the y-axis. The closer I get to 4, the closer my output values are getting to the number 2. And on the limit on the left, I would choose numbers that are a little bit less than 4, say 3.7, something like that, go up to my black graph of f of x and over the y-axis, and it looks as if the closer I get to 4 from the left, the closer the output values again get to 2. So the limit from the right is equal to 2, the limit from the left is equal to 2, and we could go ahead and say the overall limit as x approaches 4 of this function f of x appears to be equal to 2, at least roughly from the graph. Now let's see if we can find the limit as x approaches 4 of g of x. Exactly the same idea. I can start by looking at the limit as I approach 4 from values a little bit larger than 4 to the right. And remember that now if I put in a value like 4.2, I want to go up to the graph of g of x, and that is because I'm finding the limit as x approaches 4 of g of x now. And if I go up to the graph and over, I'll hit some number on the y-axis. It looks as if as I get closer to 4 from the right, the outputs are collecting around the number 10, at least roughly from the graph. And if I were to approach 4 from the left-hand side, choose something like 3.7, I have to go up to the graph of g of x now and go over to the y-axis. The closer I get to 4 from the left-hand side, the closer my outputs get to 10 again. So the limit from the right of g of x as x approaches 4 from the right is 10, and the limit as x approaches 4 from the left of g of x is equal to 10. Therefore, the overall limit exists and is equal to 10. Notice that if we were to plug 4 into g of x, we would actually get a completely different value. It looks like we would get 11 as an output value. But remember that limits, we don't care what happens at 4. We only care what happens as the x values get very close to 4. So we don't care about the fact that g of x has some completely different value when we plug 4 into it. That has nothing to do with finding the limit. So the limit of the difference of our functions is the same as the difference of the individual limits. So we were able to find those. The limit of the first one function was 2, the limit of the second function was 10, and we just want to find the difference of those two numbers, of those two limits, and we would get 2 minus 10. That would give us negative 8. What I'd like you to do is to stop the video and try part B yourself. We are referring to exactly the same functions that we have graphed here. Now you want to find the limit as x approaches 4 of this rather complicated looking function 5 times f of x divided by g of x. So take a moment and try that, and then we'll go through it together. Okay, let's try this together. We're going to go ahead and use our limit laws to break this down. I want the limit as x approaches 4 of this quotient 5f of x divided by g of x. So according to the quotient limit law, I can do the limit as x approaches 4 of the function that's in the top, that's 5f of x, and I can divide by the limit as x approaches 4 of the function that is in the bottom, which is g of x, provided this limit in the bottom is not 0. If the limit is 0 in the bottom, then we can't use the quotient limit law. There may be another way to do it, but hopefully that won't be a problem. Okay, let's look at the limit that's in the top. You notice that this is the constant 5 times f of x. We had a limit law called the limit of a constant multiple that said that we were allowed to take this constant multiple and pull it outside of the limit sign. And so that's what we're going to do. This would be the same as 5 times the limit as x approaches 4 of f of x. And that was just the constant multiple law for limits. It allows us to pull constant multiples to the outside. And in the bottom, I still have the limit as x approaches 4 of g of x. We've kind of broken this down into the simplest possible limits that we can using our limit laws, and now it just becomes a question of whether we can find these simpler limits. So I have 5 times, and we want to ask the question, can I find the limit as x approaches 4 of f of x? Well, we actually already did that. We're using exactly the same functions that we had graphed in part A, and we already found the limit as x approaches 4 of f of x. We found that that limit was equal to the number 2. So I'm going to say 5 times 2. And can we find the limit as x approaches 4 of g of x? Well, we actually already did that using the graph in part A. We said the limit as x approaches 4 of g of x was equal to the number 10. So I'm just going to go ahead and say, well, the limit in the bottom is equal to 10. And notice also that it isn't equal to 0. That would give us a problem. That would say we couldn't break up our limit this way, and we would have to find another way to find the limit. But our limit in the bottom is non-zero, and so we're allowed to use the quotient limit law to figure out this problem. And so what would we get as an answer? We just get 10 divided by 10. 5 times 2 is 10, so I would end up getting 1 as an answer to this. Okay, let's look at another limit law, which is usually referred to as the power limit law. It says the following, and again, we're going to say this without proof. We would need the precise definition of limit to prove these laws. We're going to find the limit as x approaches a of, and the function we're finding the limit of is some function f of x, all raised to the power n, where n is a positive integer. So n is something like 1, 2, 3, 4, 5, and so on. So where n is a positive integer. It turns out that this power law works over a much larger class of numbers than positive integers, but for right now we will just go ahead and say let's let n be a positive integer, so a positive whole number. Okay. What this law, power law, says is that the limit as x approaches a of f of x raised to the n, this function, is exactly the same as if we find the limit as x approaches a of just f of x and get some number and raise that whole number to the nth power. In words, we say the limit of a power is you can probably guess the rest of it is the power of the limit. So if I want the limit of a power of a function, f of x raised to the power n, I can do that by just finding the limit of the function and raising it to that particular exponent. So the limit of this power is the same as the power of the individual limit. Let's try it on a particular example. If I want the limit as x approaches 3 of x to the 4th, well, 4 is a positive integer, so I can use the power limit law, and it would be exactly the same as the limit as x approaches 3 of x, all raised to that power, to the 4th power. Of course, the question becomes, can we find this simpler limit that I have inside? And yes, we can. We've done this particular one a few times now. It's just the obvious limit. The limit as x approaches 3 of x is just the number 3. So that limit that's inside is the obvious limit, and it comes out to an answer of 3. So I'd end up with 3 raised to the 4th power. That's 3 times 3 times 3 times 3, which would be equal to 81, and that would be the answer to our original problem. A little side question that turns out to be very handy is the following. What does this mean about the limit as x approaches a of x to the n? That's the type of problem we just did where our n was equal to the number 4. Well, if I want to do the limit as x approaches a of x to the n, it is a power limit, so I could go ahead and say, well, that would be the limit of a power would be the same as the power of the limit, so that would be the same as the limit as x approaches a of x, that's our function in this case, all raised to the nth power. So I'm applying the rule that we just saw up here, number 6, the limit of a power is the power of the limit, and I'm applying it to this particular rather simple function. Instead of f of x, I have the function just x there. And the nice thing about this is that the function that's on the inside, the limit that is on the inside, I should say, is just the obvious limit. The limit as x approaches a of x, that's one we can do. It's the obvious limit. And so I find that limit, and limit as x approaches a of x is just equal to a. And then I raise that whole thing to the nth power. And so this limit inside is just the number a, and I would end up with a to the n. Kind of important for just ease of calculating things, I put down here, this means that in order to find the limit as x approaches a of x to any positive integer power n, what does it mean? It means we can just plug in, you notice that what we end up with is a to the n, and what we started out with was x to the n. We can just plug the a value that I have down here in place of the x. So I put down in this little red cloud down here, it means we can just plug in a in place of x. So we can find this limit simply by replacing the x that we see in our function with an a. Okay, well, we actually have only one more limit law to look at. So let's look at that next, and that's on the next page. And this is the last of our limit laws. It says the limit as x approaches a of the nth root of f of x is equal to, and this is very similar to the power rule, but instead of doing a power of f of x, we're taking an nth root of f of x. So the limit as x approaches a of the nth root of f of x is exactly the same as if we take the limit as x approaches a of f of x, which hopefully is something we can find, and then take the nth root of whatever number we get. And remember that the little index here, the n, is the root that we are taking. And again, we will say where n is a positive integer. And this is called the root law of limits. It says that the limit of a root is, you can probably fill in the rest, is the root of the limit. So in order to find the limit as x approaches a of the nth root of a function, we can simply find the limit as x approaches a of the function and then take the nth root of whatever number we get once we find that limit. Well, let's see how that would work in a particular example. Here I'm being asked to find the limit as x approaches 125 of the function cube root of x. So I'm taking the third root of x, and notice that my index is a positive integer 3. Well, according to my root law, the limit of the cube root of x should be exactly the same as if I find the limit of what's under the root. So I'll find the limit as x approaches 125 of x, and then I will take the cube root of the answer. Well, the question becomes, can we find this inner limit, and does it exist? Well, it's actually the obvious limit. I'm finding the limit as x approaches 125 of x. So what's inside is one of our two building block limits. It's the obvious limit, and we know that the limit as x approaches 125 of x is just the number that we are approaching, 125. So the limit as x approaches 125 of the cube root of x is the same thing as the cube root of 125. That happens to be a perfect cube. 125 is 5 times 5 times 5, or 5 cubed. And so the cube root of 125 is equal to 5. And that would be the answer to our original problem. Let's go ahead and write down kind of a corollary to this root theorem that we have up here. And that will be our very last limit law. The limit as x approaches a of the nth root of x, where instead of having an f of x here, I just have the very simple function x. Well, according to this root law, that should be the same thing as if I pull this limit sign inside underneath the radical symbol, and I find the limit of what's inside first. The limit as x approaches a of x, and then take the nth root of that. Well, what's inside is the obvious limit again. It's the limit as x approaches a of just the function x, and we know by our building block limit, our obvious limit, that this limit can be found by just replacing the x with an a. So limit as x approaches a of x is just equal to a. And so the limit as x approaches a of the nth root of this very simple function, just x, ends up being the nth root of a. And I put in a little red cloud over here. What does that mean we can do in order to find this limit? All we really did, if you look at it, is we took this function, the nth root of x, and we ended up replacing the x with the number that x was getting close to. We just replaced the x in this expression with the number a. We ended up with the nth root of a. So I'll just write down here, it means that we can just plug a in for the x in our original function. So if I just replaced this x with an a, I would have gotten the correct answer, the nth root of a. All right, I want us to look at a rather important example.